You know what else?
All right, yesterday we were talking about limits.
Infinity.
What do you remember about limits? Does it, okay, it's kind of a, by that I think we're saying that it's not really where, we talked about the ant, right? It's not where the ant actually is, it's where he anticipates being, right? And so this ant, it's actually a pretty helpful model, as hokey as it is. We said something like, even if a dense calculus fog rolled in and he's walking along the function, the limit is where, even though he can't see, he can sense. He's got that ability to sense his x and y coordinates. It's where he anticipates stepping when he gets to a certain x value. Now the function, does it need to exist there? No, it doesn't. Could it exist there? Sure, it might. Usually it probably does, but it doesn't need to. And the example we took specifically was this guy right here. Right, was this f of x equals x cubed minus 1 over x minus 1, and we even graphed that. And I don't think I left a graph of it up here, but we can make one. That's going to be, let's see. Okay, so it's going to look like this. It's going to look something like this. But, oops, we decided that there was a little place at 1 where it was undefined, right? And here was our function. We were taking the limit of that as x approached 1. And the way we write that, by the way, I'm going to get into more, we'll spend just a little bit of time tomorrow being a little more formal with what we mean by a limit. But for now, and actually for 99.9% of the class, this is how we're always going to write and talk about a limit. We would talk about this, oh, first let me write it out. Yeah, let me write this out first, and then I'll show you the notation. These are the words we would use to describe it. We would say the limit of f of x as x approaches 1. And the way we write that would be like this. Just LIM for limit. And then f of x, or I could, even if I want to write the function, I could say the limit of x cubed minus 1 over x minus 1 as x, that's bad arrow, I gotta get this so it looks good, as x approaches 1. And that little arrow to the right just means in calculus, or in math, that just means approaches, okay? And looking at our graph, function didn't exist there. Any idea what we might call that little spot where the function is undefined? It's just kind of, we're getting to a point in math where, I don't know, maybe the mathematicians at this point had just gotten so good with all that math that they just kind of, I don't know, they name things very unmathematically sometimes. What are we supposed to call that? Probably looking for some big profound words. Just a hole. That's what we call it. It's a hole in the function. Where there's a single point that's missing, we call that a hole. And if the ant stepped there, who knows where he goes, some other dimension or something. But the limit doesn't depend on the function existing there. It just depends on the ant anticipating that he's going to land on a certain spot. And we're going to get a little tighter with our definition. We're going to say that the ant definition of the limit now says that if two calculus ants, were approaching this x value from either direction, one from the left and one from the right, in order for that limit to make sense in calculus, they would have to both anticipate stepping on the same place. That make sense? Or maybe a single ant going first from the left and then from the right. It could be one or two, you decide. But the point is, that regardless of the direction you're traveling, you have to anticipate stepping on the same spot. Okay, for that limit to be, as we'd say in calculus, for that limit to exist, those are the ant conditions that would have to hold. Now later on, we'll define these in non-ant terms, just in more mathematical terms. But for now, the ant terms work great because it really does capture the essence of what a limit's all about. Okay, so what did we say the answer was there? 3. Okay, as x approaches, did I do this right? X approaches, well, oh, that's what we got. Yeah, it was 3, wasn't it? So I didn't graph it very well, but you get the idea. So the limit of this function as x approaches 1 is equal to 3. Now what does that 3 mean? Based on our picture? Yeah, and be a little bit more specific. As x approaches 1, what is approaching 3?
Y.
The y value, exactly, the value of the function. He anticipates a functional value of 3. Does that make sense? When he anticipates stepping on x equals 1, he's thinking he's going to step on y equals 3, right? So that's the value of our limit. It's just what the function, he thinks the function is going to be at, okay? That one was a little bit tricky because we had to, yesterday we relied on either the graph itself, better graph on our calculator, or we made that little table, remember? We're going to start talking very shortly about some ways that we could do this without having to rely on hokey methods like that. Could we do this in an algebra-based analytic way? And we can. There are some good techniques for that, and that's what we're going to move to very shortly. That was a little tricky, though. That one was a little tricky because the function didn't actually exist there. When we tried to evaluate this thing directly, and I'm trying to use the right terms here, when we tried to plug in the value directly into our function, we ended up getting 0 over 0, which we're going to talk about a little more rigorously soon, and that's one of 3 kinds of results we can get. And whenever we end up with something like 0 over 0, you correctly label that as undefined. What we're going to associate that with always now is more work. We got to do something to figure out that was indeterminate. It didn't tell us the answer, so we got to try something different to get the answer. Sometimes it works out better than that, though. What about this case right here? What if I asked you to take this function right here and take the limit of this function as x approaches 2? How'd you get that so quick?
Yesterday.
Oh, we did it yesterday. Oh, I should have picked a different one. Pretend you hadn't seen it yesterday, though. This is a case, if I'd picked a different number, this is a case where we can get the answer quickly. And why is this one different than this one? Okay, because this time the function does exist there. There is no hole. If I go to x equals 2, y equals 7 up there somewhere, where the ant anticipates stepping, just fortunately, is where he actually will step. And that's a really easy point to determine just by evaluating the function there. Make sense? Okay. So this time we lucked out. This is just equal to, if I evaluate this at 2, because f of 2 is 2 cubed minus 1 over 2 minus 1, which is 7, that's where he's going to be. He's not going to get tricked this time. He's going to step where he thinks he's going to step. Okay, make sense? All right, now I got a challenge for you. If we define, and let's just think strictly in terms of our ant definition for the moment. If we're going to define a limit as existing where calculus ants approaching from the left and the right would both anticipate stepping in the same place, can you think of any kinds of generic places on functions where limits could not exist then, based on that definition? And why don't you think about this at your tables for a second. So you got to go join a group here.